So to wrap up this section, we're going to look at one more test. This one's called the root test. It says if a sub n is any series, and we're going to look at the limit as n approaches infinity of the nth root of the absolute value of term a sub n, and we're going to look at what that limit equals. And we're going to again call that rho, and it's going to work much the same as the ratio test. If rho is less than 1, the series converges absolutely. If rho is greater than 1, it diverges, and the test is inconclusive if rho equals 1. And we're going to look at a couple examples of how this works. So for the first one here, we're given the series from n equals 1 to infinity, 7 over 2n plus 5 to the nth power. So using the root test, we have the limit as n goes to infinity of the nth root of the absolute value of this a sub n term. So we've got 7 over 2n plus 5 to the nth power. Now, since the n values are all positive, this term is going to be positive, so we can drop the absolute value bars. And I'm going to look at the numerator and denominator separately. So we've got the limit as n goes to infinity of the nth root of 7, and then the nth root of 2n plus 5 to the n is just 2n plus 5. Now, as n goes to infinity, the nth root of 7 is going to go to 1, and that goes back to Theorem 5 from section 10.1. I don't know if you remember, but I said those are going to come in very handy, and comes in handy here. So the numerator is going to go to 1. As n goes to infinity, the denominator goes to infinity. So we've got 1 over infinity, which is just 0. So here our rho value is 0, so our series converges absolutely. Now our second one here, we're given the series from n equals 1 to infinity of negative 1 to the n power times 1 minus 3 over n to the nth power. So once again, I'm going to use the root test. So we're going to look at the limit as n goes to infinity of the nth root of the absolute value of negative 1 to the n, 1 minus 3 over n to the nth power. Now for the first time, our absolute values bars are going to do something here. Since we're looking at the absolute value of this, the negative 1 to the n, we're just going to look at it being a positive 1. That's what the absolute value bars are going to do. So the negative 1 to the n is going to it's going to look like it disappears, but again, it's because of the absolute value. 1 minus 3 over n to the nth power. We're looking at the absolute value of that, because this could also be, if n is 1, for instance, this could be negative. So the nth root of the absolute value of 1 minus 3 to the n to the nth power, the nth root, the nth power will cancel out, so we're just left with the absolute value of 1 minus 3 to the n, or sorry, 3 over n, I apologize. As n goes to infinity, this fraction is going to go to 0, so the limit here is just 1. Now, when that rho value is 1, the test is inconclusive. So we've done the root test. However, it's inconclusive, so we need to look at something else. So what I'm going to look at is the nth term test. So I'm going to look at the absolute value of the nth term here, and I'm going to look at the limit of that nth term as n goes to infinity. And let me write all this, and then I'll talk about how this is going to work. The nth term test says if a series converges, its nth term is going to go to 0. If the nth term does not go to 0, the series diverges. So we have -1 to the n in the absolute value bars, which again, the absolute value bars are just going to turn that into a +1, so we don't need to worry about that first part. We're going to focus on the second part here. So we're looking at the limit the absolute value of 1 minus 3 over n to the nth, oops, there we go, to the nth power. Again, by Theorem 5 in section 10.1, we know that this limit is equal to e to the third power, which is certainly not 0. So again, the nth term test says if a series converges, its nth term goes to 0. Here, the nth term does not go to 0, so the series diverges. And so our ratio and root tests are very useful, but they do have limitations, and here is showing one of them. Now we're going to look at one last example. It says the series here goes from n equals 1 to infinity. It's n to the nth power over 2 to the n squared power. So one more time, we're going to look at the limit as n goes to infinity of the nth root of the absolute value of this term. Now, in this case, since n values are positive, all of the terms are going to be positive, so I can drop my absolute value bars. When I take the nth root of n to the n power, I'm just left with an n. The nth root of 2 to the n squared power is just going to be 2 to the nth power. So this is going to look a lot simpler. We're going to have the limit as n goes to infinity of n over 2 to the n. Now, if you take the limit as it stands right now, you just get infinity over infinity. So we can use L'Hopital's rule. So we just take the derivative of the numerator and denominator, and that's going to give us the limit as n goes to infinity of 1 over 2 to the n times the natural log of 2. Again, just taking derivative of top and bottom. The denominator then is going to go to infinity. 1 over infinity equals 0. Since that row value 0 is less than 1, the series converges absolutely. Now in this case, let me write this out so I don't miswrite something, trying to talk and write at the same time. When I use L'Hopital's rule here, it gave us the definitive answer that the limit here is 0. But 2 to the nth power, that exponent, that gets larger faster than just the n value. And if you know that, then you know that the limit is going to be 0, and you could possibly just skip this step here. But technically, that is the next step, though I know occasionally I will skip it myself. That's going to wrap up section 10.5, which ends the first unit that we're going to cover on chapter 10. In unit 6, we'll look at the second half of chapter 10.